Hello everyone. I'm Saptarshi Pal and I'm a PhD candidate at IIT Kanpur in the Department of Mechanical Engineering, and I'll be taking a series of lectures on the topic of continuum mechanics. So first of all, I would like to get started on why I am interested in this subject and why I think it would be helpful for everybody to at least have an idea of this subject, or how the thinking how do we think about things in this subject. So first of all, I would like to start with what is continuum mechanics. So the most of the content that I will be covering today is an excerpt from a paper by, sorry, this is the first time I am teaching this course or teaching any course, so it may get a little clumsy. So I'd be thankful if you bear with me. So yeah, so the thing I'm going to read today is an excerpt from a paper called Continuum Theory of Defects. This was a talk given by Ekkehart Kröner in a conference in 1980 called as the Physics of Defects. So I'll read the excerpt and I will explain things as I go along. So what is continuum mechanics? Continuum mechanics deals with the mechanical behavior of materials modeled as continuous mass rather than discrete particles. So, for example, when we look at the structure of a solid, we'll find that uh, it's a collection of atoms placed at certain distances from each other, right? So, in a continuum theory, we look at it as a continuous mass. So, moving on, in a continuum or field theory, the quantities of interest are given in form of continuous functions of position. These functions may have discontinuities at points. So, for example, all solids in nature have defects. For example, this atom may be missing, or there might be a line of atoms here inserted in between these two planes. So, these functions may have discontinuities at points, lines, or surfaces, but these discontinuities should appear in a reasonably small number in order to preserve the macroscopic continuity of the situation. So next we would look at an example where such a discrete system is converted into a continuum theory. A continuum theory is established for a discrete system. So this would be the continuum theory of Bravais lattices as mass points. So what are Bravais lattices? A Breve lattice is an infinite array of discrete points, this is given in Wikipedia, generated by a set of discrete translation operations described in 3D space by this function. And R is equal to, R is the position of any point, the infinite array of discrete points mentioned, which is given as n1a1 plus n2a2 plus n3a3, where ni are integers and ai, which are vectors. These are called as primitive translational vectors, which lie in different directions. So for an example, we can take this to be our a1, a2, a3. So linear 3D basis, where a1 is equal to our e1, which is I cap, we all know it as I cap, a2 as e2, a j cap in the y direction, a3 as e3, k cap in the z direction, x, y, z. These vectors need not necessarily be mutually perpendicular. They can lie in any direction. So for example, this would be also a collection of a1, a2, a3. And so what this Bravais lattice describes is some structure such as this. So suppose we take the mutually perpendicular uh, translational vectors. So one point here, one point here, one point here. Along this another point. So these would be our infinite array of points described by, and these all are integers. So this is 1, this is 2, this is also 1, this is also 1. So, so every point is described as n1 a1 plus n2 a2 plus n3 a3. In this case, it's n1 e1 plus n2 e2 plus n3 e3. So this, so basically a Bravais lattice can be taken to be a perfect lattice, which is it doesn't have any defect free. None of the atoms are missing from their, none of the particles or none of the points are missing from their position. So suppose we try to develop a continuum theory of Bravais lattices of mass points. So in this case, so at every point, as every point described by R is equal to n1 a1 plus n2 a2 plus n3 a3, every point we have an atom, and the lattice is referred to as a crystal. The cohesion of the crystal, that is the atoms, are held together by the action of underground electrons, which manifest in this continuum theory in the form of interatomic potentials. So for example, an interatomic potential between an atom at R1 and an atom at R2 can be described as V as a function of R2 minus R1, just the distance between them. This would be an interatomic potential. This is also known as the pairwise potential. that only two atoms are considered in this potential. So such interatomic potentials ensure that in each configuration of the atoms, so for the given Bravais lattice, we can have different configurations. So each configuration has a well-defined potential energy, which is also called as the elastic energy. Remember that we are only talking about a solid here, which would have an accompanying elastic energy. So this energy, which is a function of atomic coordinates, is postulated to be of such a nature that the crystal assumes its perfect unstressed state when no external forces act on the atoms. So there are no stresses developed between the atoms when there are no external forces acting on the crystal. There are external forces, these are zero. So there is no stress between them. So deviation from this state, which is the perfect unstressed state, occur via deformations. Deformation would entail these distances changing. So a deformed state would be like something like this. This distance and this distance are no longer same. This would be a deformed state. So deformations then lead to states of the crystal, the description of which in a quantitative language is an important part of the continuum theory. That is, describing these deformations is an important part of the continuum description in a quantitative way. For example, in terms of strain. So in deformed state, the crystal is built up from straight atomic lines. So this is just for this example, uh, the crystal is built up from straight atomic chains, which are arranged into parallel atomic planes, forming a 3D atomic lattice. So for developing a continuum theory, a limiting process is required to transform this crystal, the discrete crystal, into a continuum. So there are two main features of this limiting process. First is that this process consists of repeated sub-processes, and these sub-processes are carried out in such a way that the mass points are split up into smaller particles, which are arranged such that in any volume delta V, always the same type of lattice, only with smaller lattice spacings, is preserved. So for example, we have for a delta V, this kind of structure, this kind of lattice. So when we zoom into it, we take a part and zoom into it, we would get the same distribution of atoms, same orientation, same lattice. So this is the idea of fractals. So where we zoom in and whatever part we zoom in, we get the same type of structure. Only these spacings would be smaller as compared to these. The second feature would be we would want for a given volume delta V uh, taken from the whole lattice, the delta M to remain the same. So that when we shrink the volume delta V to 0, it ends up giving us a mass density dm by dv, which is defined as limit delta V tends to 0, delta M by delta V. So this these two features makes it make it clear that the theory which is developed in this manner, the continuum theory, describes well only those phenomena which can be described as large scale phenomena. That is, if we keep on shrinking, if by these processes we keep on shrinking the volume delta V, we would eventually end up at the discrete atoms, right? But that is not what we are looking for. So we operate at such a scale, such a length scale and such a time scale, that when we take smaller and smaller portions of the uh, continuum continuum, we get the same structure. So for this example, in particularly this example, the continuum which is constructed by the above limiting process, which the first feature which was the lattice remains the same upon shrinking the volume delta V, and the second is that the delta M in any delta V, if all the if the whole structure is divided into delta in volume elements delta V, delta M is same, and shrinking delta V to an infinitesimal volume gives us a mass density. We these two processes, these features of the process preserve the crystallographic directions of the lattice. Crystallographic directions are preserved, which can be observed experimentally with optical or electron optical means before, during, and after any deformation. So, thus an orientation called the lattice orientation of the elements of delta V, of the elements delta V, of the continuum can be measured with respect to some reference orientation. So, for example, suppose delta V has a structure like this. So these are the three crystallographic directions. So any volume delta V, these these directions would be observable experimentally with respect to some, say suppose this is the reference orientation we have. These three can be measured. And since this relative lattice orientation can be measured without reference to any history, that is any path we take to obtain this volume delta V, we would get the same lattice orientation. So that means that these crystallographic directions have the physical status of a state quantity, that they are not dependent upon the path uh, which was taken to obtain them. And this quantity these crystallographic directions must be determined if one aims at a complete description of the state of the body, complete continuum description. So this is opposed to the isotropic elasticity theory, which does not require the lattice orientation to be defined. Next we come, so after this example, next we come why we need continuum mechanics. So as we saw in the above example, it is difficult to keep track of the varied quantities, position, momentum, energy, etc. of each individual atom in the lattice. So if we take the discrete description, so it would be very cumbersome to keep track of position, say x, momentum, energy of each particle, of each individual atom in the lattice. Therefore, rigorous mathematical tools are made use of to convert such a discrete description into quantities described as fields, which are continuous functions of position and time. So, for example, the momentum can be described as a function of position and time. Energy can also be described in a similar way. So, these are called fields. And taking taking a time independent theory for the moment, the laws of differential calculus permit us to consider such continuous functions of position as noticeably constant over the infinitesimal volume element. That is, for a given infinitesimal volume delta V tends to 0, suppose this is the volume element, these quantities can be taken to be noticeably constant. That is, they don't vary over this infinitesimal volume element. And the relevant quantities on the infinitesimal scale of the volume element can be investigated and then connected to those of the neighboring elements. In this way, establishing laws which apply over the whole medium. A good continuum theory which takes into account the relevant aspects of the behavior of the material, for example, the crystallographic directions in the example given before, it permits us to obtain solutions for the state of the body which are of comparable accuracy with less effort. These are elegant in form and easy to overlook and understand. So next, uh, I'll give an overview of what we will study in this course. So first of all, there are 5 major things. So we'll start with the preliminaries, which is tensor algebra, where we will look at descriptions of points, vectors and tensors. So that as we have looked in the previous slide, that we deal with quantities like quantities like energy, which is a scalar, quantities like momentum, which is a vector, and also quantities we will see which like stress and strain, which are tensors, second order tensors. So these are given as functions of position and time within the body. So we will use differential calculus to predict to have to have equations like the equilibrium equations, which describe the which is a balance law of the body, balance law of force of the body. So for these, we would need to understand how we what are points, vectors, tensors, and how we use them. What are their features? What are their properties? And we will, in this chapter, we will also look at some representation theorems of such quantities. The second thing would be tensor analysis. So in this, we will look at differentiation of such quantities, of the aforementioned quantities, points, scalars, vectors, tensors. And we'll look at a few special derivatives such as gradients, divergence, and curl. And we'll also look at theorems such as the divergence, theorem, Stokes theorem, and localization theorem. The third thing we will be looking at is kinematics. Kinematics is basically the description of deformation and motion of the body. The fourth thing would be balance laws, where we'll look at the concepts of force and moment, and linear and the conservation laws pertaining to linear and angular momentum. Linear and angular momentum balance laws, their conservation laws. Using concepts of force and moment. The last but not the least, we'll be looking at constitutive assumptions. Which is basically the description of material behavior. So in this, we will look at how to describe whether a material is solid or liquid or any other, or suppose we take an elastic material. So how do we describe it? How that relation between the stresses generated in the body and the deformation is described. So for example, Hooke's law of linear elasticity is a constitutive assumption. And we will also look at, under this topic, the material response, indifference of material response to change in observer, that is, if the observer change, if the observer's orientation or if the observer's frame changes, the material response which is observed should not change. Also, if the scope is there, we will look at some simple examples such as linear elasticity or inviscid fluids, which exemplify the thinking which goes behind developing continuum theories. The main references for this course are two books, one by Chadwick. The book is named Continuum Mechanics, Concise Theory and Problems. And the second one, which I'll be following closely, is by Gurtin, which is titled as An Introduction to Continuum Mechanics. So the way I'll be conducting this course is that I will go through the chapters one by one, and then after every chapter or within every chapter, wherever I feel the need, I will be solving, I will be taking a lecture to solve some problems related to that, so that we get an idea of how so this doesn't just remain a spectator sport, and we will be solving problems to see how the theory works. We'll see the theory in action. So what I personally think about continuum mechanics and what I have personally learned over the years during my time at IIT Kanpur about continuum mechanics, what I've taken out of it, is particularly the thinking. That this course has really taught me to think in a very structured manner. So first we will list out what our assumptions are. So what our assumptions are about the material, about the frame, about the description of the fields we have previously mentioned. Then we list out from the what we want from what is the description that we want from the assumptions we have taken. And everything, there are not much things to be remembered here. Everything is followed as a logical uh, process, that after the assumptions, this is what we need. So for example, uh, in a given body, the assumption is that the body follows the Hooke's law, that is, stress is linearly proportional to strain. So given this relation, how would we now describe what are the limitations to a body? So can we describe different sorts of behavior with this law or not? So these things come out very naturally uh, with this way of thinking. So that's all for today. We will see you in the next lecture. I will be posting the links to these books to these books in the description below, and also a link to the paper, link to the conference proceeding from which I described uh, from which I gave an introduction to continuum mechanics. This one. Thank you.